My name is Alex Conway, and I'm a finishing PhD student at Rutgers University. And this summer, I'm going to be starting at VMware Research. So, unsurprisingly, this talk is going to be about how to copy files. But when I say files, what I really mean are any sort of file system structures. So it can be files, directories, or directory subtrees. So copying file system data is a ubiquitous operation, and it's important. And when you copy, this can sort of be an explicit thing by calling a utility like CP or CP-R, but you also have file copies when you're making backups, or perhaps less obviously when you do something like start a virtual machine from a template. And one particular workload that's interesting here is container instantiation, because in container instantiation you do a copy, and that copy can be a substantial performance bottleneck for that. So traditionally, file systems do not provide an explicit copy operation. So when you want to make a copy in a file system, what you often end up doing is you do a physical copy. You read all the file data from the files, and you create some new files, and you write that file data into them. So the problem with doing this physical copy is that it's very high latency. You have to do all the work of reading the files and writing them back out again, and you end up using a lot of space because you end up with 2 copies of all of your data. So a little bit more recently, several file systems have begun to implement a logical copy. So for example, Btrfs uses a copy on write B tree as its underlying data structure, and it can leverage that in order to implement a sort of shallow copy where you don't copy the file data, you just copy the metadata. And you can do this with CP-reflink. So XFS and ZFS also offer sort of similar logical copies. So this sort of copy on write has the advantage over physical copy that has much lower latency, and it can have much better space use. But as we're going to see over the next few slides, this better space use can come at the expense of high fragmentation, and there's a sort of trade-off that happens there. So we can see that in the following benchmark. Suppose that we take, if we take 64 4-megabyte files that we fill with random data, and we perform a benchmark over a series of rounds, where in each round we logically copy all the files, and then we change just a small little bit of each file. So we change 16 bytes. We do a total of 1 kilobyte of changes across all these files, and we look at the amount of space amplification that we have, that we get. So space amplification here is the amount of extra space that the file system uses over the amount of changes that we've made. And as you can see, even with this logical copy, Btrfs and ZFS use over 100 times as much space as the amount of changes that we've made. XFS does a little bit better, about 30 times as much space. We can also measure the fragmentation that the file system that we get. And so here what we're measuring is the fragmentation over the latest copy that we've made. We can measure fragmentation by timing the amount of time it takes to perform a grep over that latest copy. So in this plot here, the y-axis is the amount of time that it takes to perform that grep, and the x-axis is the number of copies that we've made so far, the number of rounds of this benchmark. And as you can see, both XFS and ZFS show more fragmentation as we continue making copies and making small changes to those copies. So what we see here is that these file systems either have a large amount of space amplification, or they end up having high fragmentation over time. So what kind of performance would we like to have out of a logical copy operation? Well, some of the things we'd like are specific to copying. So we want our copies to be space efficient and not use extra space. And we also want them to be low latency. So when we do the copy, we don't want to take a lot of time. We also want our copies to preserve the general file system performance. And so this sort of means not just, if we make a whole bunch of copies, say like 100 copies, we want the original file to have fast reads and fast writes. We want the 100th file to have fast reads and fast writes. And we want the 50th copy right in the middle to also have fast reads and fast writes. And this really comes down to locality. We want to have locality of all of these, of any amount of copies that we want to make. So the contribution of this paper is a high-performance logical copy implementation that we made in Btrfs. So Btrfs is a file system which is based on copy on write B epsilon trees, and we leverage this underlying data structure in order to do this. So if we look at our performance goals, this logical copy implementation is going to satisfy all of them. It's going to be a space-efficient, low-latency copy that supports fast reads and fast writes across any of the copies that we make. So what is the challenge of doing a logical copy? Well, let's do an example of what happens when you do logical copy in an inode file system. So this is a very simple file system here. It has two files in the root directory, /foo and /fred, and these files have some data blocks. So here, this folder icon indicates a directory inode, and we have the two file inodes for the files, and they have some data blocks. So if we want to copy /foo to /bar, what we can do is we can make a copy of foo's inode. And that inode is going to have references to the data blocks of foo. And this is roughly what the file systems that I mentioned before do when they implement their logical copies. It's some variation on this sort of simple idea. Now, we can look at our performance targets and ask which of these it satisfies. Now, we've managed to copy all the data of this file /foo to /bar just by creating a single inode. And so this is sort of obviously a very low latency operation. So that's great. And at first glance, this looks like it's very space efficient, right? We've copied potentially arbitrarily many, the data of arbitrarily many data blocks just by copying this inode. However, if we start to make some modifications to our file system, say we want to change a bit to a data block of /bar, well, what are we going to have to do? Well, in order to do this, we're going to have to copy that data block over to a new one and change the bit, and then relink it up to the inode of /bar. And the problem here is that we've added a whole data block to change a single bit. And in general, these data blocks are going to be at least 4 kilobytes, and they can be more. But if we wanted this to be really space efficient, we'd want these to actually be as small as possible. And so in the worst case here, this is not going to be a space efficient copy, at least. Okay, so let's look at the fast reads and fast writes. So in general, most file systems offer no strong locality guarantees between data blocks. Now, in general, file systems do use some sorts of heuristics in order to keep data localized co-located on disk. And that may work reasonably well on the originals, but as we start making a bunch of copies with small changes, it's going to be very difficult to keep the changed data blocks of these copies co-located with the original data. And so in general, we really only have locality guarantees if the data blocks are large. Now, again, these are usually 4 kilobytes, and on most storage devices, this is going to be too small for locality. So in general, we're not going to have locality, and so we can't guarantee fast reads and fast writes. And so this gets at the following trade-off. If we use larger blocks for our data, we'd have a larger copy granularity, and that would give us better locality of data, because they'd be kept in these large blocks, but we'd have worse space efficiency. If we use smaller data blocks, then we're naturally going to have worse locality of data, but we're going to have better space efficiency. And the sort of thing that we tend to use in general is something like 4 kilobyte blocks. And the problem with 4 kilobyte blocks is that they're too large to have good space efficiency, but they're too small to have good locality. And the problem isn't really with 4 kilobyte blocks at all. It's not that that's the wrong choice. It's that there isn't really a good choice. If we go larger, we're going to have better locality, or we're going to have worse space efficiency. If we go smaller, we're going to have worse locality. So the takeaway from this example is by creating a DAG out of this inode tree, we were able to share data across copies, and we were able to do so in a very low latency way. But the problem and the challenge to doing things this way is that as soon as we start making some small writes, this is sort of fragile, and it's easy to break sharing sharing of data blocks between copies. So our solution to this problem is a new data structure called the B epsilon DAG. So we've been working on a research file system called BetterFS over several years, and BetterFS is based on a data structure called the B epsilon tree. What we did in this work is we took the B epsilon tree and we turned it into a B epsilon DAG, which enabled us to provide fast logical copies. We'll see how in a second. So the insight for why this works is that B epsilon trees have good locality and batch together small writes. And we want to use this batching together of small writes to avoid breaking sharing between data blocks, between copies. So in this paper, we turned B epsilon trees into B epsilon DAGs to share data between files while maintaining all the good properties that we get with B epsilon trees. So at this point, I'm going to do a sort of quick review on how B epsilon trees work. So a B epsilon tree is a search tree, sort of like a B tree. But where in a B tree, all the internal nodes of the tree are packed full of pivots, in a B epsilon tree, each internal node has a few pivots, and the rest of the node is used as a buffer. So this particular B epsilon tree contains the data of a simple file system that I've sort of put a logical diagram of here on the left. And so in this file system, we have a root directory, and we have 5 subdirectories of the root, each of which is named after a color. So we have /blue, /green, /orange, /red, and /violet. And some of these directories have some files in them. So for example, we have /orange/A, which is represented in this figure on the right by this orange file labeled A. And the data for that file is stored in the B epsilon tree on the right in this orange rectangle labeled A in the middle leaf here. So, right. Okay. So now suppose we want to add a new file to the file system, say /orange/D. What we're going to do is we're just going to put the data for that file into the root, the buffer of the root. And now we've added it to the file system. And suppose we want to add some more files, say /blue/Z, /orange/F, and /violet/B. Okay, so we've added some files to our file system, and now at this point, the buffer of the root node is full. So what do? We're out of buffer room. Well, what we do is we pick the child of the root that's receiving the most messages, and we move those messages to the child's buffer. So note that when we do this flush operation here, this is sort of internal to the B epsilon tree, and the file system structure on the left here doesn't change. So now we've made some more room in the root, and we can add some more file data. So now we can add, say, /green/L and /orange/T, and we filled up the root again, and we're going to repeat this process. So again, we pick the child that's receiving the most messages, we flush into that child. Now this child's buffer is full, we can pick the child receiving the most messages and move them down. And this process can cascade down the tree until eventually it reaches the leaves. So the key insight about this algorithm here is that every time each flush that we perform, so key insight here is that each buffer accumulates a collection of small changes, and then those are applied all at once in a single flush. Okay, so let's see how we can implement a logical copy by changing these beta epsilon trees into beta epsilon DAGs. So here's a beta epsilon tree, and suppose we want to copy /green to /red. So let's just suppose that all the data in this tree for the /green directory is kept somewhere in this tree below this node here. So this node covers the whole /green subtree. So every /green file is somewhere down here. Now note, there might be some other stuff in this subtree as well. Perhaps, as you can see, this node has some data for /blue/L, but let's not worry about that. So what we'd like to do is we'd like to logically copy this /green, all the data in /green to /red by adding this edge here. And then if we go to look up stuff in /red, we'll follow this path here on the right, and we'll get to all the stuff in the subtree, and we'll have shared it successfully. But there's a problem here. The problem is, if we do a lookup for, say, /red/m, which does exist in this subtree, when we get to the subtree itself, it's not going to see anything labeled /red/m. It's going to see stuff labeled /green/m, and so on. So the solution to this is we're going to include a prefix translation in the pivots. So it can be null, but in this case, we can just add a translation that says, hey, if you're a lookup looking for /red and you cross over this pivot, stop looking for /red, start looking for /green. Okay, so we can just sort of run through a quick example. So suppose we want to read the data in the file /red/m. The way this works is we're going to start by looking in the root for /red/m, and we don't find anything in the root called /red/m. So we're going to look at the pivots and follow them down to the correct child, which is this one on the right. So now we look for /red/m in this child, and again we don't find anything labeled /red/m. So we're going to follow the pivots down, and it's going to take us to this node down here at the bottom. But because we cross this pivot with this prefix translation, instead of looking for /red/m, we're going to start looking for /green/m. And indeed, we find /green/m, and we can return its data and successfully complete the request. OK, so this is the rough idea of how we are going to do logical copy with B epsilon DAGs. Let's look at what happens when we start performing some small writes after making a copy. So here's the same B epsilon DAG that I just had up, where we've copied /green to /red. What happens when we start making some small writes to /red? So let's create a file /red/b. Well, first off, we just put that file into the root. So we've added /red/b by just adding this message to the root, and we haven't broken any of the sharing so far, right? But what happens when we keep adding messages? Well, as we keep adding messages, they're going to flush down the tree, and eventually we're going to get to a point where we want to flush into this shared subtree. So how are we going to do that? Well, the idea is we're going to flush with a copy on write. And this is a sort of complicated process, so I'm going to break it down into a bunch of steps. The first thing we're going to do is we're going to copy the node itself. Once we've copied the node, we have a node here that has some of the data that we want, but it doesn't have the right keys anymore, and we don't want the data here to be /green data anymore. We want it to be /red data. So we apply the translation that we have in the pivot, and we translate everything from green to red. So now we have this /blue/L data here that's unreachable along this path, so we don't need to include it anymore. So we can just delete it out. Finally, the pivot translation no longer makes sense. We don't want to translate along this top pivot. We want to translate along these pivots that go into the shared green subtree. So we move the pivot translation down. And now we're ready to flush this data down into this node. So I know there's a sort of a lot going on here, right? And you don't have to follow all of this. But the fundamental idea here is that we've applied multiple small changes all at once. And we've done this by only breaking sharing of a single node. If we were to keep adding data, we would continue to break sharing algorithmically going down this subtree. And after we've broken this single node, we're still sharing the rest of the subtree, right? So we call this whole process copy on abundant write, because we're doing a copy on write process where we're only doing we're only actually performing the copying on write, and we're only actually breaking sharing when we have a lot of writes that we're going to apply. So let's revisit our performance goals and look at what we have with B to epsilon logical copy and B to epsilon DAGs. So we sort of get for free the stuff on the right, because B to epsilon trees have large nodes, and that guarantees us a high amount of locality. We go into great detail in this in our FAST 17 paper, File Systems Fated for Senescence, Nonsense as Science. But with copy on abundant write, we also have space efficiency, because this copy on abundant write process gives us an algorithmic upper bound on how much extra space we can use per unit of new data. So I would also argue that right now we already have a low latency copy operation. Now we can go in and we can sort of surgically add this edge into our data structure. But we can actually do better than that. We can reduce the copy latency in B to epsilon DAGs even further. So let's look at this B to epsilon tree here, and suppose we want to copy /green to /violet. So something I sort of glossed over before is there might be some data that's sort of en route to this node that covers the green subtree here. So for example, there's this /green/L sitting in the node. And this is sort of one of the strengths of B to epsilon trees, is that data can be sitting in flight somewhere up the tree, and it will sort of move down the tree algorithmically as it needs to. Well, so what we have to do first is we have to move this data down to this node. Next thing that we're going to do is we're going to insert a go-to message. Now, a go-to message is a new kind of message. Generally, when you have messages in B to epsilon trees or LSMs, these are messages that change the data that's stored in the tree. So you might insert some new data, update some data, or delete some data, things like that. A go-to message does something a little bit different. It changes the structure of the tree. So a go-to message functions as a pivot. It's a message that functions as a pivot, and it could potentially even do prefix translation. So I've stuck this sort of go-to message in the root, and it points to this node down here. It's highlighted in yellow. So the idea is when a lookup message finds a go-to message, it can skip directly to the target. So if we're trying to read the data of a file /violet/h, we start by looking in the root. We'd find this go-to message here for /violet. We say, aha, we're going to skip to its target along this path. And there's a prefix translation here from /violet to /green. So we're going to end up just skipping down to this node here and looking for /green/h. And then eventually further down, we might actually find the data /green/h. OK, so this functions just like a pivot in the example I showed before, but it also functions like a message. So if we start to add some data to the tree, we insert some more data, it can flush down the tree just like a regular message. If we keep going and adding some more file data, eventually it'll make its way down till it gets to its correct height. And its correct height is 1 plus its sort of correct height is the height 1 plus the height of its target plus 1. And at this point, it's going to become a real pivot. So we just translate a real pivot. And we're sort of back in the situation we went through before. And here, if we were to keep flushing data, eventually we would break the copy on write again. And this is sort of important that it becomes a real pivot because this maintains the guarantee that you never go back up the tree. So you don't want to be going sideways or back up. You want to go down so that lookups never have more than logarithmic cost. OK. So if we look at our performance goals again, with go-to messages, we definitely have a low latency logical copy. So if we return to our original space amplification and fragmentation micro benchmark here, you can see where we've added betterfs with logical copy via B epsilon DAGs. The betterfs isn't subject to this locality, the space locality trade-off. It has both low space amplification and low fragmentation. And we can look at the latency required to perform these copies. So in this plot, we just are taking the wall clock time it takes to perform the logical copy itself, and that's on the y-axis, and the x-axis is the number of copies that we performed. And as you can see, betterfs has very low copy latency. Now, we've also done a whole bunch of file system micro benchmarks. So these are sequential read, sequential write micro benchmarks. And I know there's sort of a lot going on here, but the sort of takeaway from this slide is that across these micro benchmarks, I should say, the B epsilon DAGs and logical copy are implemented in betterfs 0.5. And you can see that compared to the last version of betterfs and other file systems, betterfs 0.5 has roughly equivalent performance to betterfs 0.4. We've also run a whole bunch of application benchmarks, and it's sort of the same story, where the performance is roughly equivalent. And here, as you can see in red, we've also performed some of these on copies of files. And you basically get roughly the same performance as without the logical copy implementation. So the conclusion here is by using B epsilon DAGs, we can transform the copy on write operations into copy on abundant write operations. And these give us strong bounds on space amplification while preserving locality, even if we make a bunch of small changes. And they do so by exploiting the B epsilon tree's natural batching and flushing algorithms. B epsilon DAGs preserve the good properties of B epsilon trees, fast reads and fast writes. They preserve the logarithmic tree height guarantee and query cost. They preserve the asymptotic costs of inserts and updates. And we can also give fast and cheap logical copies using go-to messages and so on. When we evaluate betterfs with B epsilon DAGs in practice, we have strong copy performance, low space amplification with low fragmentation, good locality, low latency copying. And B epsilon DAGs preserve the good performance of betterfs on other operations as well. All right, thank you very much.
All right, thank you very much for the presentation. We have time for a few more questions.
For the, you had this translation message from red to green.
Yep.
So those are, that prefix is stored for every file that gets copied? Like, what prevents you from finding, if you have a translation from red to green, finding like a file you didn't copy? Like R, I searched for red R, but it's only green R. Like, what prevents me from somehow finding files I didn't copy with these links.
Well, after you do the translation, you're going to be looking for /greenr in that subtree, right? And if that doesn't exist, you're not going to find anything. Right?
I guess I'm just trying to, you create this new link. Does that link only allow you to find that one specific file, or can you somehow find now all the files that were in that other directory?
Well, so the link is only going to translate that particular prefix, right? And to get to that link at all, you have to be looking for something with that prefix. So
can you maybe go to like?
I think the answer to the question is the translation is on the entire thing you copied. If you only copy /red/r, the translation will be on all of /red/r.
Only for R.
In that
Yeah.
case, it's red.
Okay.
So it's that thing.
Okay, so if I make 1 million files in the same directory, I just have up 1 million of these translations.
if I'm following you,
No.
No.
Okay, can you go to the picture where you have
Sure.
your tree?
If you copy the entire directory, it'll just be a translation for red to green. But if you copy each file, it's just a translation for.
Each file. Okay, that answers my question. Thanks.
Okay. Ethan?
Ethan Miller, UC Santa Cruz. So when you're measuring latency, is it latency for the B epsilon trees until all the operations are done, or just you put it in at the top and I'll do the rest of it in the background?
well, so it's not measuring stuff that's happening in the background. It's the latency to do everything to get it to that point. But we do this enough times that all that sort of background, sort of what you're calling background stuff, will actually happen as part of the experiment.
In other words, you are including that, but you're amortizing it across the multiple operations.
We are including the amortized cost across multiple operations. So it's sort of an average, right?
Yumesh?
Okay, Umesh Mashwari from Hewlett Packard Enterprise. So you mentioned that 4 kilobyte is too small for locality
Yep.
and too large for space efficiency. On SSDs, though, it comes close to, good enough for read locality at least. And one can argue that nothing is large enough for write locality, given the way the flash blocks are increasing. So that's one part. And on the other side, I think you use an example where the bytes changing, there are only 16 bytes changing, and I was wondering whether it's sort of too artificial, too small.
So, I mean, to answer your first question, if you have a device like an NVMe device or something that has, good performance on, say 4 kilobyte random reads, then sure, you don't have to worry about this. If you're on, a commodity SSD of some kind, you might not have that guarantee, right? So you're right that sort of part isn't going to apply to all hardware. In terms of your second question, yeah, that's sort of a fair cop. But there are workloads that are going to do sort of random small writes. You can have virtual machines that are running things. You can have, say, stuff like, suppose you have a database and you're making small updates. These things can happen. I mean, here's the thing: if your application is very well behaved and it's doing nice 4 kilobyte granularity writes, then yeah, you're totally fine. But like in general, applications aren't going to be that friendly, right? They're not going to do exactly that. I mean, you have to talk about specific applications too.
You're thinking indexes of kinds? Is that what you're thinking? Indexes, database indexes?
Well, indexes is certainly an example that would do that.
Okay, thanks.
All right, one last question.
Hi.
Please go ahead.
Juan from Amazon.
Hi.
I wanted to understand your experimental results, but I feel that I need to know what the size of these BDAG blocks are and what is the cost of the flush operation with respect to a regular block on the other file systems.
So the nodes in a B epsilon tree, the ones that we use are usually 2 megabytes or 4 megabytes, depending on the exact storage that we're using. I mean, 4 megabytes is a reasonable approximation.
Okay, this ones, right?
Yeah, these are all 4 megabytes big, and we flush when the node fills full of data, when there's no room, no logical room left.
So you're flushing 2 megabytes, right?
When we're flushing, well, so it has there's a certain fan out to the node, right, depending on how many pivots it has, and we're going to flush at least the amount of data in the node over the fan out, because we're going to pick the child that's receiving the most data. So there's some guarantee it's something like 512 kilobytes or something per flush.
Yeah, so it could have been that I made a 4K block 30 and then that cost a 2 megabyte flush, and so that kind of appears as random delays on your operations. I
Yeah,
guess,
there's
right?
it's an amortized, the whole structure is amortized,
Yeah,
right? So
that's
you
what
can
I-
have sort of tail latency stuff like this. That is possible.
All right, thanks.
You're welcome.
All right, thanks for the great presentation. I'd like to thank
you.
the speaker again.